Welcome to this lecture series in real analysis. In this lecture, we will discuss the convexity of the exponential function and prove as a result the arithmetic geometric mean inequality. So let's recall the definitions and a key theorem. This is the definition of a convex function. I do not want to spend time on it. You can pause the video and read it. And this automatically upgrades to a seemingly stronger looking condition, namely this one. Again, you can pause the video and read it. So this is basically the definition of convexity. The key theorem that we need is the fact that if you have a function defined on an interval to the reals, which is twice differentiable and which has the property that its double derivative is always non-negative, then the function is convex. So this we saw earlier at some point. And along with that, we will also need at least these two properties of the exponential function, which is the first one is that the exponential function is a bijection between the reals and the positive reals. And this is what I call the homomorphism property. It converts addition to product. All right, great. And recall, the definition of the exponential function was that it is a function which is its own derivative and which takes the value 1 at 0. All right. So first, a very simple lemma that the exponential function is convex. And we will just use the double derivative test. Since the exponential function is its own derivative, it is also its own double derivative. And we also know that the exponential function is always positive. It is a bijection between reals and positive reals. So the double derivative is always positive and hence always non-negative in particular. And therefore, by the criterion for convexity that we just recalled, we see that the exponential function is convex. So that is trivial. Before we go to the arithmetic geometric mean inequality, let's prove a very simple statement about the exponential function, which should have been perhaps discussed before or given as an exercise, but no harm in doing it here. So we are saying that if you exponentiate something divided by n, that is same as raising or taking the nth root of the exponentiation. So take x, a real number, exponentiate x upon n, or exponentiate x and take the nth root. Nth roots we have discussed earlier. The nth root function is a function from non-negative reals to non-negative reals, and it is also a bijection if n is at least 1. If n is 0, then it's a constant function. Right, so we can talk, if n is 0, then you can't define 1 upon n. So anyway, forget about that. The nth root map is a well-defined map from positive reals to positive reals, and it is a bijection. So this is a well-defined quantity, and we want to show that these two things are equal. Again, this is very simple, just a simple application of the homomorphism property. So we have that exponential of x by n multiplied with itself n times is nothing but, by the homomorphism property, the exponential of the sum of all these arguments, which is the exponential of x. So we see that the nth power of the exponential of x by n is the exponential of x. And since both of these numbers are positive, this and that are positive numbers, this implies that the exponential of x upon n is the nth root of the exponential of x. Very simple. All right, so now let's get to the arithmetic geometric mean inequality. So suppose we have positive reals a1 up to an, then we claim this inequality happens. The left side is called the arithmetic mean and the right side is called the geometric mean. Since these are positive numbers, we can take the nth root of the product, because when you're taking nth roots, you cannot, suppose n were an even number and this happened to be a negative number, then this wouldn't be well defined, but we have taken everything to be positive, so everything is well defined. And yeah, this is a very popular and famous inequality that you must have seen at some point before, and maybe you have seen a proof of it before, but perhaps you haven't seen this proof. This is also a very standard proof, but before you discuss convexity, this is not something that you see. All right, so let's just prove it. So since each ai is positive, we can find real numbers x1 up to xn such that ak is exponential of xk for each k. Right? Because the exponential function is a bijection between reals and positive reals. Every positive real, therefore, can be expressed as the exponential of something, and not just something, a unique something, but that's not relevant here. So we have that. And now, so by the convexity of the exponential function, we see that this is at most that. Right, all we are doing is taking lambda 1 as 1 by n, lambda 2 as 1 by n, and so on up to lambda n as 1 by n. So these lambdas sum up to, let me write that again. So the lambdas sum up to 1 because each of them is 1 by n, and therefore by convexity of the exponential function we have this. So just be convinced. And the left side is nothing but the product of the various exponentials by the homomorphism property. And the right side is the average of the exponentials. Right? But what we discussed in the previous page was that this is the nth root of the exponential of x1 and so on. So the left side becomes that, and the right side stays as it was. Okay, and now just use the fact that this is a1 up to this is an, and that's it. So that gives a1 to the power 1 by n dot an to the power 1 by n is at most the average. Great. This is same as that thing, and that finishes the proof. So this is a very nice short proof of the arithmetic geometric mean inequality, which is not obvious. It is not so easy to prove this. Anyway, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.